All right, let's dive right in. We're going to a world so tiny you could never, ever see it with your own eyes. The world of nanotechnology. Now, when scientists point these incredibly powerful electron microscopes at crystals, they see these just beautiful, complex patterns. But these are way more than just pretty pictures. They actually hold the secrets to how a material is built, atom by atom.
So that's the big question, isn't it? How in the world do you map a landscape you can't see? How do you predict the patterns that will show up inside a world that exists on an atomic scale? Well, let's find out. To get our heads around this, we're going to go on what you could call a nanoscale safari. And just like any safari, the very first thing you need to know is what you're actually looking for. And in this case, we're on the hunt for something called lattice fringes. You can kind of think of them as the stripes on a tiny, tiny nanoscale zebra. These lines you see, they're not random at all. They show you the exact direction the crystal's atoms are pointing. They are the landmarks on our tiny map. So when scientists are peering into these microscopes, they're basically looking for one of three things. You might see a single set of these fringes, just simple parallel lines. You could see what they call cross fringes, where two of those sets of lines intersect. Or you might see, well, nothing, just a plain, patternless area. Being able to predict which one you're going to see is absolutely crucial.
Okay, but how on earth do you predict that? Scientists don't just point their very expensive microscopes and, hope for the best. Turns out they have this incredibly cool tool that brings us to our next stop, the crystal visibility map.
This map is really the key to the whole thing. It's a tool that tells a researcher exactly what pattern to expect, all depending on the angle they're looking at the crystal from. It's kind of like having a cheat sheet for the Nanoverse. The best way to get your head around this is to think about a regular globe of the Earth, right? You can spin it, you can point to any spot, and you know immediately if you're looking at an ocean or a continent. A crystal's visibility map works the exact same way. Every single point on its surface is a different way of looking at the crystal, and the map tells you if that specific view is going to show you single fringes, cross fringes, or nothing at all.
Now, for the specific crystals in this research, they're called face-centered cubic crystals. Things like gold and aluminum have this structure. It just so happens that their visibility map is a perfect sphere. Super elegant, really simple shape. But as you're about to see, that beautiful simplicity, well, it creates a surprisingly tough problem.
And that right there, that's the core of our story. We've got this perfect globe that maps out our crystal, but how do we get actual, precise numbers from it? How do you take a globe and turn it into a flat, usable map? So, I know what you might be thinking. What's the big deal? A sphere sounds pretty easy to work with, but here's the thing about doing precise math. Curves can be a real headache.
The problem is that calculating the exact surface area of some weird, complex shape that's drawn on a curved surface is, well, it's notoriously difficult. I mean, imagine trying to figure out the precise area of Brazil by using a flat ruler on a school globe. It's a total geometric nightmare. And hey, don't just take my word for it. The researchers themselves say it plainly in their paper. It is a well-known difficulty. So the very thing that makes the map so elegant, its perfect spherical shape, is also what makes it a huge mathematical challenge. So how did they crack this puzzle? Well, instead of trying to solve the impossibly complex math head-on, they came up with this really clever geometric shortcut. First, they focused in on just the tricky little areas where the different pattern regions meet. Then, and this is the genius part, they basically just said, hey, what if we pretend those little curved patches are simple flat shapes, like little squares and parallelograms? It's way easier to calculate the area of a flat square, right? So they did that, and then they just subtracted that simple area from the bigger region. It's an approximation, sure, but it turns out to be a stunningly effective one. So, what did this clever shortcut actually get them? Well, it let them do something that sounds simple, but is actually huge. They could calculate the exact odds, the probability of seeing any one of those patterns just by looking at a crystal from a totally random direction. And here are the numbers they came up with. Using their simple flat shape math, they figured out that if you look at a random nanocrystal of this type, you've got a 55% chance of seeing single fringes. You've got a 15% chance of seeing those rare cross fringes,
and a 30% chance of seeing no fringes at all. And look, this is way more than just a math problem. What this does is give scientists a vital statistical baseline. If they're looking at a sample with thousands of these nanoparticles, they now have this powerful predictive tool. They know what the mix of patterns should look like. And this is where we get to the real payoff. What do you do with this new knowledge? Well, this is where the map leads us to the actual nanoscale treasure. To really get why this matters, let's compare their geometry model to what you could call a paint model. The paint model is basically a powerful supercomputer simulation that brute forces the problem. It literally paints the map pixel by pixel and then counts them up. It's incredibly powerful, but it takes a lot of computer power. Their shortcut, on the other hand, is fast, it's elegant, and it's the perfect tool to quickly check and verify the results from those bigger, more complex computer models. Now, they did find there's a sweet spot for this. Their method is super accurate, especially for particles that have a thickness to size ratio that's greater than about 3 nanometers. It's a specific detail, but it's an important one that tells scientists exactly where this tool works best. So when you put it all together, this simple calculation really is a treasure map for scientists. It lets them double-check their big computer models super fast. It helps them spot tiny structural flaws, because if the patterns they see don't match that 55, 15, 30% probability, they know something might be different about that crystal structure. It even helps them estimate how much of a nanoparticle is perfectly formed. And that just leaves us with this one final thought. We just saw how a problem that seems incredibly complex, mapping things on a quantum scale, was basically solved with high school geometry. It really makes you wonder, right? What other giant scientific problems out there are just waiting for a solution, not with more computing power, but just with a simpler, more clever map?